Hello everyone, welcome to our channel Simplified Computer Science Concepts by Professor Rutuja. Today we will be learning deadlock detection algorithm in distributed systems, that is Obermarcks path pushing algorithm. So here let us consider this illustration of Obermarcks path pushing algorithm wherein there are 4 sites. Each site will have processes into it, and let's say here site 1 A is waiting for the resource that is been allocated to B. Similarly, B is waiting for the resource that is allocated to the external process, that is C, which is on site 2. C is waiting for D. D is waiting for E, which is placed externally on site 3. Or we can say D is waiting for an external process E. E is waiting for F. F for G, which is external. G for H, and H is again waiting for A, wherein A is external to H. So this is just a scenario of distributed systems that is given over here. And now in path pushing algorithm, when we say path is nothing but just the flow of information, and pushing means nothing but sending. So this information is sent via a string from one side to other side. So we send this path information in the form of string to each other from one side to another side. So prior to that, each site maintains a local wait for graph. So here let us consider this site 1, A and B. So for this we require we have taken one external node named as x. By x, because to maintain a local graph for this particular site, we require this external node x. Why? Because A is waiting for some process which is external to it, that is placed on site 4. So instead of for maintaining a local graph, we have taken this x. Then B is waiting for a process C, which is external to it. So again, to represent that, this x is there. So similarly to all the sites it will apply. The x node is nothing but a virtual node which is used, or which helps us to maintain the local wait for a graph, wherein the processes that are waiting for some external resources are represented over here. Now each site is maintaining its local wait for a graph in the form of strings. Now this strings that is generated will be sent from one site to another site. So here if I just want to generate a local wait for graph and convert it into the string and send it to the other side, it will be x a b coming back to x. Why? Because x a is waiting for external site which is H. That is why it will start from x, then it will go to A, then B, and again B is waiting for some external process, that is C. So again x, that is why external. This is how for each site the string is maintained. If I want to transfer from site 2 to site 3, it will be x c d x, x c D coming back to x, because D is waiting for external process. Then again from site 3 to site 4, the message would be XEF, and from site 4 back to site 1, it will be XGHX. Now here just look at the first string and the second and the last string. The first string is XABX and the last string is XGHX. There is no similarity, which means that there is no deadlock. Now this again we have to push this path again. So in level 2 we will push the path again. So after the local data structure of each site is updated, this updated wait for a graph is then passed along to all the other sites, and this procedure of pushing is repeated. So initially site 1 is going to send this information XABX to the second site. Now here, the most important thing is whenever site 2 will send a message to site 3, the message will be consolidated message of site 1 and site 2. So here if you see, it is just the concatenation of site 1 and site 2, wherein site 1 said x abx and earlier site 2 message was x cdx. Now here the concatenation of site 1 and site 2 messages there, that is x abcdx. Similarly, from 3 to 4 it will be x cd f x. Why? Because earlier two sites we are considering. So which are the earlier two sites? That is c d e f. So for this fourth site, second and third site we will consider and push the path. Now from 4 to 1, earlier two sites. Which are the earlier two sites? That is ef gh. So ef gh path will be pushed to the first site. Now again compare this. The AB, XAB, X, XAB, X, and the last message that is received from site 4 to site 1 is XEFGH. That is not common. So here again deadlock is not detected. So we have to push the path once again. So after pushing the path, obviously the first site will send the same message. The second site will send the concatenated message of site 1 and site 2. The third site will message. Now here you will find a difference. This third site will now push a message or a string which is concatenation of site 1, 2 and 3. Right? So it is x, a, b, c, d, e, f, x. And now when site 4 is sending message to site 1, it will be a concatenated string of site 4, 3 and 2. So 3 levels are now pushed. That means x, c, d, e, f, g, h, x. Again compare the first string and the last string. There is no common strings or there is no common sites into it. So no deadlock. So we have to push the path once again. Now the same thing will happen. X abx, concatenated x abcdx, then x abcdef. All the 3 sites have concatenated, and the last one for the fourth level it will be x abcdefg x. Now here just compare first and the last one. Yes, we are finding something common, that is AB over here and this is also AB over here. So there is a cycle detected, and there is a obviously when there is a cycle, a deadlock is detected. Now there might be a question coming to your mind, till how many times we are going to repeat this? Unless and until something we get in common, we will keep on repeating this to discover the deadlock into this distributed systems. So we are simply pushing the path as a string and finding out whether a deadlock is there or not. So that's it, which is related to Obermarcks path pushing algorithm. Thank you everyone for watching the video. Please like, do share and subscribe to the channel Simplified Computer Science Concepts by Professor Rutuja. If you have any comments, please do post in the comment box. Thank you everyone.